In our previous lesson, we learned about binary search and we also implemented binary search, but we implemented an iterative version of binary search in which we used loop to write our program. Now in this lesson, we will write binary search using recursion. Let us first quickly write an iterative version of binary search. So I will write a method binary search that will take as argument a sorted array A, the size of the array n, and an element x that is to be searched for. Then we initialize two variables, low and high, low to 0 and high to n minus 1, and we say that while low is less than or equal to high, calculate middle index as low plus high upon 2. It's a better practice to calculate mid as low plus high minus low upon 2, which is the same thing except that we are not calculating low plus high. Sometimes low and high individually are within the range of an integer variable, but high plus low overflows the range or limit of an integer variable. Now there are three conditions. If x is equal to the middle element, we have found x in the array, so our search is over. We return the index mid and exit. Else if x is less than the mid element, we adjust high to mid minus 1 to say that we discard anything which is on or after mid because x is less than the middle element and the array is sorted. Else if x is greater than a mid, which should be implicit here for the third condition, as the third condition. In this case we set low as mid plus 1. And if we come out of this while loop without finding anything, we return minus 1 to say that x does not exist in the array A. What we are essentially doing here is that if we have an array in which elements are in increasing order, then we first compare x with the middle element, and if x is equal to the middle element, it's fine. If x is less than the middle element, it must exist before this element in this highlighted section, and if x is greater, it must exist after the middle element in this particular highlighted section. And we keep on repeating this process in the new segment until either we find x or we cannot divide the search space any further. At low equal high, our search space becomes, or rather reduces to size 1, reduces to only one element. After that, we cannot divide it any further. Binary search is a typical example of a divide and conquer algorithm in which at each step we are dividing the problem into half. Let us now write recursive implementation. So once again, I will write a method binary search that will take a sorted array A, and this time the arguments will change a little. We will take two arguments, low and high, to mark the segment of the array in which x may lie at any stage. X is the element to be searched for, and the logic would be something like, once again we will calculate the mid index, and then we will have three conditions. If we find x, that's good, we return the index at which we have found it. If x is less than a mid, we call binary search recursively on the range low, and I'm running short of space here, so I'll create some space here, and we will run we will call binary search recursively for index low to mid minus 1. So x is now to be searched between index low to mid minus 1. Else if x is greater than a mid, which will be the third condition anyway, we will return binary search from mid plus 1 to high. So we make a recursive call to search x from index mid plus 1 till high. When we write recursion, we should always look for a base case, a base condition where we would stop our recursion. In this case, we will stop our recursion if we find the element. So this case will return and exit, and we will not make any further recursive call. But what if we do not find the element? What if we do not find x in the array? We have another base condition for that where we need to exit. If low is greater than high, then we do not have a valid segment in the array, and in this case we can say that we have exhausted our search space, so we return minus 1 to say that x does not exist in the array. I'm short of space here, so I'm writing these two statements in the same line. So these two are our base conditions that would cause the recursion to stop or exit. And this condition low greater than high is the same condition which we are checking here to stop the loop. Let us now quickly simulate this recursion using an example. Let's say we have this array A, a sorted array of size 9, and we want to search for number 63 in this array. So we make a call to the function binary search, and I will write BS here as shortcut for binary search. Okay, we pass to the function the array A, and lower index should be 0 and higher index should be 8 to say that initially the number can exist anywhere in the array from index 0 to 8, and the number to be searched for is 63. Now we go inside the function. Is low greater than high? No. So we go ahead and calculate mid. Mid would be calculated as 4. The element at index mid, index 4, is 36, and 63 is greater than 36. So we come to this else condition, the third condition, and we make a recursive call to search for 63 within range. Mid plus 1 would be 5 to 8. Now once again, for this function, low greater than high is not true. So we calculate mid. Mid would be 6 if we take only the integral part. And element at index 6 is 63. So we have found this element. We will return mid. So we return 6 here. And this method finishes. And this method also returns 6 to its caller, maybe the main method. Let us now say that we want to search for number 25. So we make this call to binary search from the main method. Now once again we calculate the mid. Now element at index 36 is greater than 25. So we make a recursive call to search for 25 from index 0 to 3. Okay, now is low greater than high? Is 0 greater than 3? No. So we go ahead and calculate mid. Mid would be 1. Element at index 1 is 6. 25 is greater than 6. So we make a recursive call to search for 25 between indices 2 and 3. Now mid would be 2, and this time we will make a recursive call to find 25 in the range 3 to 3. It's still a valid range. Low is not greater than high. Mid would be 3. And now 25 is greater than 21. So we make a recursive call using the third condition to mid plus 1 would be 4, and high would be 3 still. And this time low is greater than high. So we come to this condition where this method simply returns -1 and finishes. Now this method also returns -1, and this gets propagated all the way up. And finally this method returns -1 to its caller, the main method. While writing recursion, we must be very careful about the base conditions. Like we have these two base conditions here. If we do not get our base conditions right, our recursion may go on endlessly, causing the program's memory to overflow and causing it to crash. The time complexity of this algorithm is big O of log n. The time taken is proportional to log n, and this comes from the fact that if we keep dividing the size of the array by 2 at each step, then it will take us log n steps to reach array size equal to 1. Now one obvious question, which one is better, the recursive implementation, a recursive implementation, or an iterative implementation? Well, anything that we can write using recursion, we can write it using iteration, and anything we can write using iteration, we can write it using recursion. Iteration is a slightly more performant, it's better in performance because we do not have to store all these states of all these functions, the extra functions in the memory. But writing recursion may sometimes be very intuitive and easy to write. For most practical reasons, you may choose any of these according to your comfort. So that's not an issue. Okay, so this was recursive implementation of binary search for you. Thanks for watching.